activities that we were looking at the beginning of class could be considered pre-reading for that text we look at. The text that we read is just really about charged and neutral particles. But it also starts to get into this idea of polarization. In a substance like a pane of glass or a wall, it might have a balance of negative and positive charges and be neutral overall, but the presence of another substance that is charged might push some of the charged particles within that substance away. Okay, so there's a couple things for us to look at here before we finish and try to answer this question about where lightning comes from. The first thing I want us to look at is that we have a couple balloons here. I'm just going to spread them around the room. Has anyone ever had the experience where you take a balloon and you rub it on a sweater, you rub it on your hair? Can we pass one to the middle over here? And then what happens with that balloon? Static?
Statics. Your hair sticks up.
Static. So let's try it a little bit, right? Try rubbing it on a sweater or try rubbing it on your hair if you don't mind. And there's a demonstration of the balloon that worked to some degree but not perfectly. If you rub a balloon on your hair or a sweater, it should stick to the wall. And the explanation for that is it's picking up negatively charged particles from your hair, and then when you put it against the wall, those negatively charged particles are pushing the negatively charged particles in the wall away and attracting the positively charged particles, which creates a connection, a force between them, and holds the balloon to the wall. So one of the things in the reading where it says is that, that all matter is made up of charged particles. In most substances, there's a balance between positive and negative charges, right? So let's think about the balloon before we started rubbing it. I started rubbing it on my head, right? So it's got all these particles in here that are negatively and positively charged. And let's say they're kind of distributed evenly. Does this balloon have a charge overall right now when you look at it?
Yeah.
It's neutral. Why is it neutral?
Even.
Even number of negative and positive charges, right? So when I rub it on my hair, what I'm actually doing, well, one of the things I'm doing is I'm moving negatively charged particles to the surface of the balloon from my hair. They're electrons. So one of the things that's important to know about positive and negatively charged particles is the negative ones move much more easily than the positive ones. So it's very easy for the negative charged particles to move from one substance to another. And so what can we say about the balloon now? If after adding all those negatively charged particles?
Neutral.
Is it still neutral?
No. It has an electric charge of numerous.
It's got an electric charge of numerous negative particles, right? So overall it is very negative at this point. Now let's think about that glass. The glass doesn't have a charge overall. It's also neutral. What do you think might happen as we move the balloon towards that piece of glass?
They're going to attract the positives.
They're going to attract the positives. Right? So all these positives are getting this little pull. All these positives in here, right? What's happening with the negatives?
They separate.
How do the negatives feel as the balloon gets pushed towards them?
Pushing away.
They're going to get pushed away. And so in fact, they actually move. All the positive might be on this side, and then the negative gets pushed over here. And so what happens is that these negative charges, they're getting pushed a little bit, but they're not getting pushed as much as one that's right next to it here. This one might get pushed all the way over here. These might get pushed all the way over. These might get pushed all the way over. And then these that are closer, they get pushed a little bit, but not quite as far. That doesn't get pushed quite as far. And the same might be true of the positive that's getting pulled here. These are all getting pulled right next to it, right? Because it's a strong negative charge. But these maybe, it's over here. This is over here. It's not getting pulled quite as much. The negative charged atoms here connects with the positive charged particles in the glass. And so they stick. This movement of particles within a substance is called polarization. I did a diagram of the balloon in the wall so that students could see the negatively charged particles receding into the wall. It's a stair step, sort of a scaffolded step into the understanding what's happening with lightning. Now, so back to our original question. Why does lightning happen?
I think it's a discharge of negative matter or particles
lightning is a discharge. The balloon example is tangible. It's right in front of us. We can see it happen. It's actually a very similar situation to what's happening in a lightning storm, so that the bottom of the clouds and that collection of all those negative charges is actually pushing the negative charges in the house, a tree, any objects on the ground. It's making them recede into that substance. What are the negatively charged particles doing to the particles, positive and negative, in the objects on the ground?
Trying to attract the positive
They're attracting the positive
and pushing away the negative.
and pushing away the negative, right? So all the positive parts of the house are moving to the top, and the negative ones are moving to the bottom.
They supposed to be together, right? Positive and negative to balance out. So let's say you have all positive up here, all negative down here. So of course I think the negative will looking for a positive environment to become neutral, right?
They all want to be neutral, right? They all desire a positive charge, right? It's like they're looking for their partner.
But what's going wrong that they cannot connect to the positive to the other top of the ground?
So let's think about that. All these negative charges here that we know can move, right? Because we took that balloon and we picked up all these negative charges from my hair. We know these can move, and they really want to connect with the positive in the trees and in the house, right? And the positive wants to connect to the negative. And Eileen says, so why can't they connect?
That's the lightning.
They can, right? So the thing is, at some point, that we can call it desire, or whatever it is, that attraction between these two things at some point becomes so strong that it can leap over space. Where is the force strongest between the cloud and the ground?
The highest point, the tree.
The highest point, right? And why? Because it's closer. Distance matters, right? And so when the pole gets too much, there's the lightning. And what that lightning is just all those negative charges pouring into the top of that tree. And suddenly all of these, that connection happens, and all of it just starts rushing in.
Like the other rays, they're trying to like, from that thunder, they're trying to spread out.
Exactly. It's all they're like reaching out. They're looking for that positive. And you can see if you watch slow motion of the lightning. I have some other videos. If you watch in very, very, very slow motion, it's like they're going out there looking for positive connections. Is it safe to be under a tree during a lightning storm, or is that a myth?
No, it's not safe.
Can't say.
It's not safe because it's the highest point, and once that charge goes through there, it doesn't just stay in the tree, right?
Yeah.
It also shoots around the tree, right?